Welcome, developers. Let's get started. Today, we are diving into one of the most powerful extensibility features of Claude Code, custom/commands, officially known as skills. We will learn how to encapsulate your proprietary business logic, complex prompts, and formatting rules into repeatable, automated CLI commands. Let's define what custom/commands, or skills, actually are. At their core, they are user-defined instructions that extend what Claude can do. The basics are simple. You type a forward slash followed by your command name, like /deploy or /review, and Claude executes a predefined workflow. Why do we need this? Because copying and pasting your company's proprietary playbooks or formatting checklists into chat every single day is inefficient. How do we fix this? We create a skill.md file, and Claude automatically adds it to its toolkit. For our deep dive, it's crucial to understand progressive disclosure. If we put all our workflows into our main system prompt, we'd bloat the context window. Instead, Claude only reads the skills metadata at startup. The heavy, detailed instructions are only injected when you actually type the /command. Take a look at this execution flow. When a user types a custom /command, it hits the Claude Code CLI. Because of the progressive disclosure pattern, highlighted in orange, the system dynamically reaches out to load the full skill.md content right at that moment. Finally, it executes your proprietary workflow using that freshly injected context. To build a custom command, we must understand the architecture and directory setup. What does this involve? It's the specific file hierarchy required to register the command. The basics dictate that project-level skills live inside a.claude/skills/directory at the root of your project. Why do we use this directory? Because it tightly scopes the logic to the repository, allowing your entire team to share the custom commands through version control. How do you set it up? You create a folder named after your command, for example, commit code, and inside it, you must place a file strictly named skill.md. In our deep dive, let's dissect the skill.md file itself. It consists of two distinct parts, YAML front matter at the very top, enclosed by dashes, which defines the metadata, and the markdown body below it, which holds the actual execution prompt. This mind map illustrates the required folder structure. Inside your project repository, you have the .claude directory. Within that, the skills folder acts as the registry. Each subfolder, like commit code or format YAML, defines a unique /command. Inside each of those folders sits the mandatory skill.md file, split cleanly into YAML front matter and the markdown prompt. Let's explore front matter and invocation control. What is this? These are the configuration parameters written in YAML that govern the command's behavior. The basics require you to define a name and a description. Claude uses this description to understand the skill's purpose. Why is this critical? Because by default, Claude is highly autonomous and might trigger your skill on its own if it deems it relevant to the conversation. For harmless commands, this is fine. But how do we prevent Claude from running destructive commands? We use the disable model invocation flag and set it to true. For our deep dive, understand that if you write a /command for /deploy or /drop database, you absolutely must use this flag. It strips the model's autonomy, guaranteeing the proprietary workflow only executes when a human explicitly types the /command. Look at this invocation decision tree. Once a skill is registered, the system checks the disable model invocation flag. If true, it routes left to manual only, requiring a human to type the /command. This green node represents a safe environment for deployments and actions with side effects. If false, it routes right, allowing Claude to auto-trigger the skill, which is great for reference tasks, but risky for infrastructure changes. To make our commands truly flexible, we must master passing arguments for dynamic execution. What is this? It's the process of injecting runtime user input directly into the prompt. The basics revolve around the $arguments placeholder. Why do we do this? Because hard-coding a file name or a JIRA ticket number makes the command useless for anything else. Arguments make your proprietary logic reusable. How does it work in practice? If your prompt contains the placeholder and a user types /fixissue123, the system dynamically replaces the $arguments tag with the string 123. Check out the sample code on the slide. For our deep dive, notice that you can get very granular. You can access individual arguments by their index using $0 or $1. Because Claude uses shell-style quoting, if a user wraps multiple words in quotes, your skill processes it perfectly as a single variable. This sequence diagram maps the argument injection process. The user executes the command/format code followed by two quoted strings. The CLI extracts these arguments as index 0 and index 1. The prompt engine intercepts the payload, replaces the $0 and $1 placeholders inside your skill.md file with the user's strings, and finally executes the dynamically tailored prompt. Now we unlock true power, injecting dynamic context using pre-processing syntax. What does this mean? It means executing local shell commands and embedding their live output into the prompt before Claude even reads it. The basics involve prefixing an inline command with an exclamation mark like git status. Why is this revolutionary? Because proprietary business logic often depends on live data like the exact state of your Git tree or active server ports. Claude cannot guess this information. How do we provide it? We embed the command directly into the markdown. For our deep dive, it's vital to understand the execution order. This is a pre-processing step. The CLI executes your shell command locally first. The text output of that command physically replaces the placeholder in the prompt. By the time the prompt hits the Claude model, it contains the actual, live data, ready for analysis. Observe this state diagram for the pre-processing phase. When the / command is invoked, the engine scans for the bang syntax, the exclamation mark. Upon finding git diff, it halts and executes the local shell command. It captures the standard output, replaces the placeholder in the prompt with that text, and only then does it send the finalized text payload to the Claude model. When creating proprietary commands, we must enforce security. This is done through enforcing constraints with allowed tools. What is this? It's the mechanism of explicitly restricting which tools the / command can use, adhering to the principle of least privilege. The basics require adding an allowed tools key to your YAML formatter. Why is this non-negotiable? Security and focus. A / command designed to format YAML files shouldn't have network access or the ability to drop a database. How do you enforce this? You define exact tools and parameters, like bash, git commit. Check the sample YAML code. In our deep dive, we combine this with auxiliary scripts. You can place a complex Python or bash script in the same directory as your skill.md and authorize it in allowed tools. This creates a hybrid workflow where deterministic code and AI reasoning execute seamlessly under a single / command. This flowchart maps tool restriction in action. Our custom command /formatdb is executed. The engine hits the check allowed tools node. It successfully authorizes the read tool to analyze the schema and the edit tool to format the SQL. However, if the model hallucinates and attempts a network call via bash, the restricted permissions immediately block it, ensuring your environment remains secure. Let's bring this to life with a real-time, highly impactful use case, the smart committer. Scenario: an enterprise development team wants to enforce strict, proprietary git commit formatting rules across all projects. The problem is that developers are lazy and write poor commit messages. The execution: the team builds a custom / command called /commit code. Crucially, they set disable model invocation to true, so it only runs manually. For dynamic context, the prompt uses the git diff head syntax, feeding the exact code changes directly into the prompt without the user copying anything. The business logic explicitly dictates their mandatory Jira ticket formatting and tone. The outcome: a developer types /commit code, and the system autonomously analyzes the live diff, generates a perfectly compliant message, and stages the commit. You've just automated compliance. Follow the automation in this sequence diagram. The developer simply types /commit code. Instantly, the command requests the local shell to execute git diff. The shell returns the raw code changes. The command bundles these changes with the proprietary rules and sends them to the Claude engine. The engine reasons the perfect message, commands the shell to stage and commit, and returns a success message to the developer. Let's wrap up with advanced configurations and best practices. As you build complex commands, you must manage context. If your command does heavy research, set context, fork in the YAML formatter. Why? Forking runs the skill in an isolated subagent branch. This guarantees that messy tool outputs and intermediate reasoning don't pollute your main conversation history. For token budgeting, keep your skill.md files under 500 lines. If you have a massive style guide, place it in an auxiliary file and reference it only when needed. Finally, always test your custom commands across different models to ensure deterministic behavior. I invite all learners to like this video, subscribe to our channel, and visit quicktechie.com for premium certification prep. We offer massive Q&A banks, full ebooks, audiobooks, full-length training, and expert interview guides to elevate your tech career. Thank you for watching. Our final mind map summarizes your mastery toolkit for custom commands. Branching out, we prioritize isolation using context, fork, and sub-agent branching. We focus on optimization by keeping files under 500 lines and using auxiliary files. We enforce security through allowed tools and disabling model invocation. Finally, we embrace dynamic workflows using argument variables and the shell prefix syntax. Build brilliantly and build securely.